Hello everyone. Today I'm going to talk about Hedetniemi's conjecture again. Hedetniemi's conjecture, that's the subject um, of my PhD thesis. So I've been working on this problem for a long time. I'll talk about it again. The title will be Hedetniemi conjecture, chromatic Ramsey number, and fraction version. So the Hedetniemi conjecture, I'll just write it here. So the concept I defined in the other lectures, so I'll not state it again. So the conjecture states that for every graph G and H, the chromatic number of the product graph, the chromatic number of the product equals to the, this is too small, this whiteboard is too small. The chromatic number of G times H is the minimum of the chromatic number of G and the chromatic number of H. Okay, it was disproved, it was not true. But, well, this is a beautiful statement. It's clean and attractive. So that's why it has been a very famous conjecture and attracted a lot of attention. However, for this conjecture to be well known, there's some other factor. So, as I said, why this conjecture is so famous? It's clean and attractive. It's very simple. But there's another factor is that it is related to some other problems, and it was there were some famous names involved. So Hedetniemi, when he proposed this conjecture, it's in 1966. He was very young, just fresh PhD, and the conjecture was published in a technical report. So it is not easily accessed. I've never read it. I cite it in many of my papers, but I never read it because I couldn't find it. I don't know how many people have read that technical report. So then, how it became well known? This is because there were two famous names involved. It's Erdos and Lovasz. They start something that is related to this problem, and that I think that is make it well known. Before that, it was not known to many people. So what is the problem that's studied by actually the paper is by three authors: Bell, Erdos, and Lovasz. It's studied by Bell, Erdos, and Lovasz. There's some strike somewhere, but I always forget it. But where to put? Maybe it's A. Sorry. Okay, maybe it's here. Okay. What they studied this chromatic Ramsey number. Okay. So that I think that makes the problem make the conjecture well known. So sometimes people call these conjectures Hedetniemi-Lovasz or product graph conjecture. Okay, so today I'm going to talk about what are the other things involved in this conjecture. So this is related to Ramsey number. It's called chromatic Ramsey number. So this is notation introduced by Erdos. We write this symbol. So F is a graph, and put the L here. We read F L. That's G H. So what does this mean? This means that if the edges for every coloring C of the edges of this graph into two colors, say 1 and 2, and then either the color one, this is those edges. See, you can say this are the edges of color one induce a graph. This contains a copy of G as a subgraph, or the second color contains a copy of H. Okay. So in other words, say you two color the edges of F. Say you color the edges of F by red and blue. Usually, say instead of 1, 2, it's a red and blue. Then either you can find a copy of H which is red, right? All the red edges contains a subgraph which is G, or there's a blue copy of H. So there's a copy of H, all the H contained here, all the edges colored blue. So I have to emphasize this is subgraph, not induced subgraph, just subgraph. So this is the meaning of this sentence. This is the meaning of this sentence. And for example, this is usually in many the simplest meaning, for example, is that K6 else K3. Okay. That means if you color the edges of K6, the complete graph of 6 vertices by red and blue, you can either find a red triangle or blue triangle. Okay. And this is another statement. Let's look at this. This K5 does not L K3. Okay, what does this mean? This means that you can color the edges of K5 in red and blue. There's no red triangle and also no blue triangle. So let's color this way. So this is K5. I can just color this way. Okay, these are the, say, this is not red, it's black. Okay, so this is a two coloring of the edges of K5, but you cannot find any monochromatic triangle. Okay, and the Ramsey theory is about. So it's the Ramsey number. The Ramsey number is KL is the minimum n, is the minimum n such Kn else KK and KL. Okay, this is the Ramsey number. Ramsey theory is a very rich theory in combinatorics and also in some other field of mathematics. So the Ramsey is the name of a mathematician, and what he proved is that this Kn exists. Right? This is such an n. It's a finite number, but what it is, then that's a difficult problem. Okay, now. Say for example, these two statements says that okay, let's write another name. Say KRK. So this is R. K. We rate this is define this as RKK. So that means what is this? This is the minimum integer n, such that you two color the edges of Kn, you will get monochromatic copy of KK. Okay, that's the minimum. So this one says we have R3 equals 6. This is the minimum n that you color edges of K6 by two colors, you get a monochromatic triangle. But K5 does not. This is, and you know that K4 is 18, and then R5 it is no problem. That we don't know. there's an upper bound and lower bound, but we don't know the exact number. It's a very difficult problem. So for this KL, the best result is that we know with case 3, we know the magnitude 3t. This is something like t squared log t. Maybe I calculate that. It was proved by there's upper bound and lower bound. The lower bound was proved by John Hein King. His Chinese name is Jing Ding Han. Okay, so they noticed that we share same character in the name. Okay, it's good to share something with the famous people. Okay, this is about the Ramsey number. The Ramsey number, let me define the Ramsey number a different way. The Ramsey number is this one. I can define it in a different way. Okay, so I can define this Ramsey number in this way. So, or let's define the Ramsey number of graph. This is KL means for this complete graph. Let's first define the Ramsey number for general graphs. The Ramsey number of GH. Say this is defined as the minimum n such Kn else GH. Okay, and Rg is defined as the minimum. Sorry, I just write this off. G is just RGG. If the two graphs are the same, I write it as RG. So what is this RGH? It's a minimum integer n such that if you color the edges of Kn, you will find either a red copy of G or blue copy of H. Okay? And this is that you will find the monochromatic copy of H if you color the edges of Kn. Okay, so now I will define this number in a different way. So I define this. This is equivalent. So what is our GH? It can be defined in this way. It's a minimum number of vertices of the graph such that F else GH. Right? This is the same because if there's a graph that F else GH, you make it complete, then certainly it is still else GH. Right? So the minimum ones, those must be complete graphs. So you can, maybe there's some other graphs also do, but you can always choose the complete graphs. So this is the definition of the Ramsey number of GH. Okay, then this is just different way of expressing this number, but it motivates many other problems. So you try to minimize the number of vertices of such graph. Why don't you cannot minimize some other parameter of this graph? So number of vertices, just one parameter. It's a one graph parameter. Right? So I can say, oh, I'm going to minimize the number of edges. So that is the side Ramsey number. So this is then why not vertex? What is vertex? I can write edges, right? So I have found the minimum number of edges in the graph such that f else gh, and this is called the size Ramsey number. Right? And also I can say I minimize the maximum degree, because the minimum of the maximum degree of f else gh. Okay, so this is also an interesting parameter. I don't know if there's a special name for this, maximum degree Ramsey number. So actually, so these are just graph parameters. I can put any other graph parameter. Many of the graph parameters, they are still interesting. Then this comes to the parameter, what is called chromatic Ramsey number. What is that? Instead of minimizing this, I minimize the chromatic number. The chromatic number of f and f else g and h. Okay. So this is called this is the one word in the title of my talk, that is the chromatic Ramsey number. This is the chromatic Ramsey number. So we are particularly interested in the case that g equals h. So that is this is the this is the chromatic Ramsey number of G. So given the graph, and we were interested in, okay, what is the chromatic number, Ramsey chromatic number of G? Okay. And this simple observation is that this is the same as, so it depends what is G, right? So if you look at KL, say this is KL, okay? If G is a complete graph, then it doesn't make sense to say that you have to choose F to be complete, otherwise it's not going to be helpful. Okay? So in this case, this is the same as the Ramsey number. So this is, I'm not going to show that, but it is not too difficult to show this. So if G is a complete graph, then this is the same as the Ramsey number. But if G is not this complete graph, then this could be much smaller. Okay, much smaller than. Of course, it's always bounded. This is always bounded by the for any graph. This is always bounded by the Ramsey number of this graph, right? Because this is the number of vertices of the f, that is else gg, and this is the chromatic number of f of such f. So this is much smaller, usually much smaller. But for complete graph, that's the same. Okay, so this is the parameter that was studied by first studied by Burr-Erdos-Lovasz, and they are particularly interested in the following problem. Okay? They're interested in this following problem because this is about the chromatic number of f. So the question is this: if the chromatic number of G equals n, okay? So because we're talking about the Ramsey chromatic number, then certainly it's natural to fix the chromatic number of G. Suppose the chromatic number of G is n, then what could be this? Then what is the chromatic Ramsey number of G? Of course, it still depends on G, right? It's not, this is not some constant, but we're interested in the range. What could be the value of our G? Okay, so as we said, G could be complete graph Kn. If G is Kn, the chromatic number is n, and then in this case, say this, the chromatic Ramsey number of Kn is just Ramsey number of Kn. Okay, so that means if this is, we have observed already, so this is Kn, this is Kn, so this is the Ramsey number of n. Okay, and we will show that for any graph, for any, so this is one observation. This is the questions. This is one observation, and the other observation is that it is easy. We will show it. We will show it that if the chromatic number G is n, then the chromatic Ramsey number of G is always less or equal to I. So this is an upper bound. This is an upper bound. And it cannot be bigger than that. So this, I will prove it. And the next one is that it cannot be. This is one. The next one is that, and the chromatic Ramsey number of G is greater or equal to n minus 1 square plus 1. Okay, so this is, so there's a lower bound, there's an upper bound. Okay, there's a lower bound, there's upper bound. I will first show the lower bound. So suppose I have a graph, so that means, so to prove this, that means for any, if the chromatic number of F is less or equal to n minus 1 square, then F does not LGG. Okay? So that's not. So this shows that. This shows this part. G has chromatic number n. G has chromatic number n. Then we say if the chromatic number F is bounded by n minus 1 square, then this F does not LGG. So I can color. This means I can always color the edges of F, so there's no monochromatic copy of G. And this is easy. This is easy. So, so this graph, the chromatic number is n minus 1 square. So I can partition this vertex set into n minus 1 square independent sets. Right? So the independent sets, this is the independent sets. This is the independent set. And now I have this is the independent set. Altogether I have this is n minus 1 independent set. And I can partition this into n minus 1 square independent sets, and then I put another n minus 1, and then so this is again n minus 1 of them. So altogether I have n minus 1 square independent sets. Okay, this is the whole. This is the vertices of F, and the edges between the, so this is, there's no edges in each of these small potato. So the edges are either this way, or this way. And, so between them. So what I'm going to do, I'm going to color all this. I think of, I call these edges horizontal. So these edges, those edges are horizontal edges. These are horizontal edges, because that's why I arranged the independence in square, right? So n minus 1 independence in each row, there are n minus 1 rows. So each row, the edges between them, I color them red. And the edges between different rows, I call them black. Then what happens is that you look at the red subgraph. The red subgraph has chromatic number n-1, at most n-1, right? Because the red graph, so this is one component, and because there's no red edge connecting this part to any part, so this is one row. Each row is one component in the red graph, okay? And which is n-1 colorable. So the red graph is n-1 colorable, and the black graph is also n-1 colorable. This is n-1 color of the black graph. So I two color the edges of this graph. So each the colored by red and black. The black graph is n-1 chromatic colorable, and the red graph is n-1 colorable, and therefore G cannot be there, right? G has chromatic n, so it cannot be contained in as a subgraph of n-1 colorable graph. So this shows this, and therefore this proves this law bound. So if G has chromatic number n, then the chromatic Ramsey number of G is at least n-1 squared plus 1. Okay, now I'm going to show the upper bound. To show the upper bound, I will need to define some terms. One is homomorphism. Okay. Homomorphism, I write this notation, G, L's, H. Okay, so there are too many L. This is quite different from this one. Okay, this is L, there's a bracket, and this is just G times H. What this means? This means G is homomorphic to H. This means G is homomorphic to H. What does that mean? That means there is a vertex. That means there exists a function, a mapping from the vertex set of G to the vertex set of H, which is H preserving. So for every x, y in EG, fx, fy is in H. So if xy is an H, then the image is an H. And if xy is an H in G, the image is an H in H. So it's H preserving. Okay. And use this notation, it means G admits homomorphism to H. So G is homomorphic to H. And I use this to mean that this is not a homomorphic. This is not homomorphic. Okay. This is the opposite of that. Okay, then I use this. This is G is a graph. Then this is all this homomorphic image of G. This is the set of H such that G homomorphic to H. Okay. So this is all the homomorphic image of G. Okay. This is a family of graphs that G is homomorphic to it. Okay. And one observation is that G is homomorphic to Kn. This is equivalent that G is n colorable. G is n colorable. Okay. So if there's a homomorphism from G to Kn, then the vertices are partitioned into n parts. So because Kn has n vertices, right? those vertices sending going to the same vertex of Kn, they must be an independent set because there's no loop in here, so it must be H-preserving. You cannot ascend two adjacent vertices to a single vertex if the single vertex is no loop. Okay. So if there's a homomorphism, that homomorphism actually give you an n-coloring. Conversely, if an n-coloring, then you send each color class to one vertex of K1, and then that is a homomorphism because any two distinct vertices of Kn, they are adjacent. It's H-preserving. So in this sense, sometimes we call this G2 a homomorphism called the H coloring of G. Okay? H coloring of G. Okay, so now I use this for family family of graphs. For family, this is a family of graphs. We write this one. It FL's G maybe. Maybe I put a bracket here. I forgot. Okay, I put the bracket here. So right, this means what? This means that this means for any this means that this means for any 2H coloring, for any coloring of the edges of EF by two colors. There's a monochromatic. There's a monochromatic graph, which is an element of G, of this family. There's a monochromatic subgraph, which is a graph in G, which is a member, which is a graph in this family. Okay. So if this is a single graph, then this means for any 2H coloring, say if this family is a single graph G, that means you color the edges of it by two colors, you'll find a monochromatic copy of this graph G. But if this is a family of, say for example, there are two graphs, say this family contains K3 and C5, C3 and C5, then it means if you color the edges by two colors, you will either find a monochromatic copy of triangle or monochromatic copy of C5. Okay, so this is the definition of this notation. And then this is a theorem proved by in this paper by Burr-Erdos-Lovasz and Lovasz. This paper is in 1976. It's 10 years after Hedetniemi's conjecture. So that's the paper started chromatic Ramsey number. In that paper, they proved that the chromatic Ramsey number, so for any graph G, for any graph G, the chromatic Ramsey number, the chromatic Ramsey number of G equals the minimum n such that Kn else the homomorphic image of G. So the chromatic Ramsey number of G is the minimum n such that the complete graph Kn else this family of graphs. This is the homomorphic image of G. Homomorphic image of G. Okay. So let's prove this. To prove this, we have a complete graph. Okay, we have a complete graph Kn, and Kn. So that's Kn. That's right. Km bar. Okay. Maybe to write for simple, to write it in a simple way. So let's write this in this way. So what is this? This is the blow up each vertex of Kn into an independent set of size m. Okay? To be an independent size of m. So it's a multi-part. It's an m-parted. It's a complete m-parted graph where each part has size m. Okay, so it's something like this. So if n equals 3, then it's a 3-parted graph. Okay. So this is m vertices, and there's complete adjacency between each part. It's complete parted. So this is if n equals 3, and this is K3m. Okay. Okay. So now the first thing we need to do is that for every n, every m, there exists m prime such that for any two colorings, for any two colorings C of the edges of this graph, K n m prime. There's a subgraph. There's a copy. There's a copy of K n m such that the edges between any two parts, they're colored by the same color, such that for any u v belongs to Kn, and edges in this v times m, edges between v times m and the u times m, I colored the same color. I colored it the same color. Okay, what does this mean? So okay, I didn't define this one. So this is just so this is vertex v of a vertex v of Kn. So this is in Kn, and this is v times, this set is v times m, right? Just blow up the vertex v into an independent set of size m. So this is the independent set which has the first, we can think of this as first coordinate and second coordinate. The first coordinate is u is v, and the second coordinate is the m is the integer in m. Okay, so so this means that okay, let's look at this picture. So it means what? It means that, okay, so this is, say, let's say this is Km, this is M prime, okay? M prime is huge, it's huge, okay? Then I'm going to find the, you two color the edges of K and M prime. It doesn't matter how you color it, okay? You can color it arbitrarily. You arbitrarily color the edges of this graph. Then I'm going to find a subgraph of Kn, it's K and M. I'm going to find the subgraph K and M. M can be very big, but it's much smaller than M prime. So I can find the subgraph here. So I can find the M that is here, M that is here, M that is here. So they induce K and M. And in this M, say all these edges, they are colored by the same color. So this is between V times M and U times M. This is V and this is U. This is the same color. All these edges colored by the same color. And similarly, this edge is colored by the same color. But this color could be different from this color. But themselves, they are the same color. And this also, they're colored, those edges, they're colored by the same color. So this is the lemma says. The lemma says this. This is a lemma. I didn't done. Okay, this is a lemma. This is called the lemma. Okay, I hope it's clear what the lemma says. Let's repeat again. You have this graph, you arbitrarily color the edges of this graph, then I will find the copy of K and M, something like this. The edges between two blocks, two small potatoes, they are colored by the same color. And this is easy. So let's still look at the picture, draw the picture again. So how I'm going to find this subgraph. So let's still look at 3 parts. Okay, so N is 3 parts. So this is 3 parts. Okay, then I first look at these edges between these 2 parts. Okay, so these are the edges between these 2 parts, and they are colored by 2 colors. They're colored by 2 colors. So I will first look at one vertex. Look at one vertex from here, and then look at all the edges. All the edges connect this one to this second part. The edges are 2 colored, and they choose the color which is used to more than at least half of the edges. Okay, then that's a lot of them, because this is M prime of them, M prime of those. So those edges, and I can choose it as half M prime edges that are colored by the same color. Okay, so I find half of them, and these are colored by the same color. All these edges colored by the same color. Okay. And then I will just forget about this. Say I don't look at those vertices anymore. But this is still huge. Okay, M is huge, and this is still huge. So then I need to draw this a little bit bigger. So this, because I'm going to cut it again. So this is just half of this size. But then I look at the second vertex, and I just look at these edges. Look at these edges. Again, I choose a color which appeared more than half, at least half of this. Okay, and then I say, I suppose this half, say this half. Okay, this half, they are the same color. Then I remove this. I just forget about those. I just remove those. Okay, and just concentrate on these. So my graph is getting smaller and smaller. And then I do the third vertex, and look at the edges between this, and they get half again, and look at these edges, and get half again. And eventually I get get a subgraph. Then what happens is that the edges, you look from this one to here, all these edges colored by the same color, right? So all these edges are colored by this one. You look down, they're colored the same. But for different vertices, the colors may be different. There are two colors. Maybe this edge going down, it's black. This edge coming down, it's all red. So anyway, so if you just look at these vertex, they all color the same color. Okay, and then I choose. So this, I color this vertex black if all these edges going down is black, and I color this red if all these edges going down is red. And then among all these, so there's a coloring of the vertices by two colors, black and red. And there's one color which appears in more than half of the vertices. Then I choose that one. So I choose, say, for example, the black color appeared more than half. Then I just delete those red ones. Say this, I don't need you. This is red, I don't need that. This is red. I still have half remaining. I still have half remaining here. And I still have half of this vertex here. So I got the subgraph. I removed many vertices, but still remaining vertices. So okay, this is my remaining. I got it. This is remaining subgraph now. Okay. Then all these edges between these, they colored by the same color, right? Because you look at the vertex down, they color by the same color. Because I choose the top vertex, they also the same color. So now I got a subgraph. So from this K and M prime, for the K and M prime, I delete many vertices. I delete, but so I get a subgraph. All the edges between these two parts, they are colored by the same color. Okay. So, but the M prime is still huge. Even I delete the half, many times half. But the remaining graph is still huge, okay? So I don't need to worry about the number. So I may have not enough vertices, but there are still many. You just start with many, and you end up with still many. You start with many, and you end up with many. Okay? You start with many, and you start with many. Okay, then I'm going to. I concentrate on this subgraph. The vertex they're deleted permanently. Okay, and then I look at this subgraph between this, and I remove vertex again. I remove many vertices again. So I remove some vertex from here, remove some vertex here, and then all these edges between these two parts are colored by the same color. Okay, and then I look at this part and this part, and again I'm going to remove parts, and then all this become the same color. Now I got a subgraph, so which is this one. So this is my M. I got M vertex here, M vertex here, M vertex here, and this is my K and M. Okay, all these edges between two parts, they colored by the same color. They colored by the same color. So this is so I just need to know what is the color between this part and this part. All the edges are the same color. Right? So I can think of this as a single vertex. This is a single vertex. This is a single vertex. Then what is that? That is Kn. Okay? And actually, so what I get is a two-edge coloring of Kn. So it's a the resulting coloring is a two-edge coloring of Kn and blow up into K and M. So I have so what I get is a two-edge coloring of Kn. It's a two-edge coloring, two-edge coloring of Kn. And then I blow up into K and M. Right? When I blow up, that means all these edges, they keep their color. So this is a vertex, this is a vertex, and the edge between these two vertices is colored by red. When I blow it up, all the edges between these two parts become colored red. So if an arbitrary coloring of this graph, I get a graph which is colored not so random anymore. It's still you have many colorings of this type, but there's some regularity there, right? Edges between two parts, they're colored by the same color. Okay, so I can assume this M is still big because I choose this M prime so big. So after I delete so many vertices, M is still as big as you like. So you take your M, you choose your M at the beginning, and then you find this M prime. So now I have a 2H coloring of Kn, and then Kn L's homomorphic image of G. Homomorphic image of G. So that means Kn, I have a. So let's look at the homomorphism here. So let's look at say 5. That's a homomorphism to triangle. Okay. So what is? So I want to send these 5 vertices to these 3 vertices, so that this H preserving. So how do I send this? I can send these 2 vertices to here, and these 2 vertices to here. So the picture looks like this. So this sends to this is 1, 2, 3, 4, 5, and this is A, B, C, and 1, 3 to A. Say 1, 3. They sends to A. 2, 4, 2, 4, 2, 4. They sends to B, and 5 sends to C. So I draw the picture again. So it's 1, 2, 2, 3, 3, 4, 4, 5, and 1. So this is sent to. This is how I send this homomorphism from here to here. Okay, now suppose I to color the edges of Kn, I find a copy of this. This is homomorphic. So let's write. Okay, these things. So I have a monochromatic copy. Suppose G is homomorphic to H, right? G is homomorphic to H. Then I have a monochromatic copy of H. So this is a monochromatic copy of H. So this is my H, and what is H? This is my H, and it's monochromatic. So it's automatic. Say maybe something like this. Okay, this is my H. Okay, and it's monochromatic. That means the edges of the same color. The edges of the same color. Then I blew up into, so for example, this is a monochromatic copy of H in this 2 coloring of Kn, the 2H coloring. But this each vertex is blew up into an independent set of size M, right? So what I get is it's an independent set of size M. It's an independent size M. It's an independent size M. And then we know by the previous lemma, we know that all these edges between them, they color the same color. That's this one, this is the same. And all these edges now are colored by the same color. Right? All these edges now are colored by the same color. This is complete bipartite graph. They're all colored by the same color. Right? And then from here, because there's homomorphism from G to H, so what is the homomorphism? The homomorphism is that the vertices of G partition like this, maybe. So this is a vertex of H, and these are the vertices that are mapped to this vertex in H. Okay, and then you know that maybe this is just single vertex. Then you know it's H preserving. So there's no there's no H in here. H is independent set, and there may be some edges between these. Maybe some edges, or maybe yeah, okay, so maybe there's some edges here. Okay, then my M is big enough, so this is bigger than this potato here, so I can find in here a copy of G in this subgraph, right? in this graph, then this is monochromatic copy of G in this graph. Okay, so what I proved the following theorem. What is said? If G admits a homomorphism on H, if G is homomorphism to H, and the Kn else H. So if you took out the edges of Kn, you will find the monochromatic copy of H. Okay. Then this Kn, then if you then there exists M prime, such Kn, you take M prime, then this else Gg, right? Because if you blow up each vertex of Kn into independent size M prime is huge, then you end up with a subgraph which is Kn M. M is still big, but much smaller than M prime, such that all the edges between these two, they are colored the same color, and this gives a 2H coloring of Kn, and Kn give me a monochromatic copy of H. This is a monochromatic copy of H, and then from this monochromatic copy of H, but I blow up each vertex into independent size M, then I find the copy of G. This G is monochromatic. Okay. So this actually proves this theorem. So if Kn else the homomorphic image, sorry, whatever, there's a homomorphic image there, then you can go back, find the copy of G, if this is M prime is large enough. But if you, how M prime you choose, this graph, the chromatic number is N, because it's a complete M-partite graph. It's a complete M-partite graph. So therefore the chromatic number of this one is say what I prove is less or equal, but equality is also true. Okay, so it is equality, but I will not prove it now. So we just need this less or equal, but the equalities. We just need this less or equal, but equality holds. Okay, now so this shows the following. This implies that if G chromatic number of G equals N, then the chromatic Ramsey number of G is less or equal to the Ramsey number of N, right? Because G is N, that means G is homomorphic to Kn. This N is it's confusing. This N is different from that N. Okay, anyway, so I hope you understand this, because if the chromatic number is N, that means there's a homomorphism from G to Kn, Maybe I write this as K, then it's not confusing with this. So write this as K. Okay. So if the chromatic number is K, then G is homomorphic to K. So KK is in here in the image, homomorphic image of K. And then this is N, that means Kn else that's KK. And therefore the chromatic Ramsey number of G is bounded by that number. Okay, so as I said, the equality holds, but we only need this natural equality in the argument. Okay, now I just need maybe not sure. Let's say we just need this less or equal. Okay, so so this is the upper bound. Okay, so what the questions? We go back to our questions again. Go back to the questions again. So the questions is that we're interested. This was interested by Burr-Erdos-Lovasz. So if the command number of G is n, then what can be the value? The Ramsey command number of G. What can be the value of G? What can be the value of G? And what we have shown, these. We have the is less or equal to Rn, right? So that's what we have shown here. Sorry, this is K changed to N now. And we will also prove that this is greater or equal to n minus 1 square plus 1. So this is the range of the Chromatic Ramsey number of G. Chromatic Ramsey number of G. Okay. The upper bound, this is tight. This is tight. Okay, because the Chromatic number of Kn is the Ramsey number n. Okay? So Kn has Chromatic number n, and we know that this is equal to n. This is by definition. Okay? How about null bound? Okay, so the null bound is n minus 1 squared plus 1. Is this tight? That was an open problem. Asked by Burr-Erdos-Lovasz. Okay. So what could be the minimum of the Chromatic Ramsey number of a graph, where the Chromatic number of the graph is n? Okay. So we can define this again. We can define function. So that pi n this is not I forgot what notation I used. But I just invent one. That pi n equals the minimum of the Chromatic Ramsey number of G, where the Chromatic number of G is n. Okay. So from here we know that pi n is greater or equal to n minus 1 squared plus 1. So you choose the Chromatic Ramsey number of G. You choose among all those graphs whose Chromatic number equals n. And from here, so we know that this minimum, so the smallest one, if you want the smallest one is going to be bigger than this, at least n minus 1 squared plus 1. Okay, then they couldn't prove if this is tight, so they made a conjecture. So this is a conjecture. This is by Burr-Erdos and Lovasz. This is in 1976. Okay. The conjecture says pi n equals n minus 1 squared plus 1. Okay. So they just want to know if, so this, the equivalently, what this says that for each n, there is a graph whose Chromatic number is n. This Chromatic number is n. And the Chromatic Ramsey number of that graph is n minus 1 squared plus 1. Okay? We know that the Chromatic Ramsey number cannot be less than that. And this says the null bound is attained. Exactly n minus 1 squared plus 1. So they made this conjecture, and they proved that this is true, or n equals 3. So pi n pi 3 equals 3 is 2, 4 plus 1. No, okay. So this is 5 and by 4. 4 is 10. So I don't remember exactly. I think they proved pi 4 equals 10. Pi 4 equals, did they prove pi 5 by 6? Okay. So I lost my memory. Anyway, say they either prove this or they prove this. 20 equals 6, it will be 25. Okay, they prove this. They just prove this. Okay. They just prove this. If I remember it correctly. Then I prove this. So this is so I proved one more than their paper. So they proved 3, then I proved 4. I think if they proved 4, then I should prove 5, but I don't think I proved 5. Okay, so this is in my PhD thesis. This is in 1990. Did I publish it somewhere? It's published, I think it's published. If it's published, it's okay. I finished my PhD in 1990, December, and this is result is in my thesis. I think it's published, but maybe published later. It's published some later. Then eventually, in 2011, I proved this whole conjecture, so that the conjecture is true, that this pi n is indeed n minus 1 square plus 1. N minus 1 square plus 1. So this is I proved it in 2011. Okay, so now how is this related to the Hedetniemi conjecture? This is the problem that made the Hedetniemi conjecture. So this is the paper that made the Hedetniemi conjecture well known, I think. Okay, because there are two big names involved in this paper, and both Erdos and Lovasz, they are off-prize winner of mathematics, and they are the big names in mathematics. Okay, so that made this Hedetniemi conjecture well known. Now, how is this related to Hedetniemi conjecture? How is this related to Hedetniemi conjecture? So this is the relation. I'll show you the relation, and then I show you how I prove this. How I prove this. This theorem. The relation is that this conjecture. So they proved. This is what they proved. Hedetniemi's conjecture. It's a Hedetniemi's conjecture. Implies this BEL conjecture. So that is what they proved in that paper. So, okay, why is that? Okay, I take, so the proof is easy. I just want to find the graph. The chromatic number is n, and the chromatic Ramsey number is n minus 1 squared plus 1. That's what I need. Right? I just construct the n chromatic graph. What is the n chromatic graph I'm going to construct? So I take 2h coloring of the, so I take the graph, say that m equals m minus 1 square plus 1. Okay. I color the edges by 2 colors. Color the edges of Km by 2 colors. Km has 2 edge colorings, 2 edge colorings. So I color the edges of Km by 2 colors. There's a constant number of 2 colorings, right? So how many are there? There are many. There are many to each edge. So each edge. So how many two edge colorings? So each edge has 2 choices, and there say m square edges. M square divided by 2 edges, and 2 to the m square edges. So there are many two edge colorings of this graph. But it's a finite number. I just listed, right? This colorings is C1, C2, and CQ. So these are all these 2 edge colorings of this complete graph Km. All these colorings. Now, for each of these colorings, so Ci is 2 edge coloring. That's not general. So it's Ci, and then the last one is CQ. So take an arbitrary 2 edge coloring of this graph. So it's colored by red and blue. So there's one monochromatic subgraph. The chromatic number is at least n, and the chromatic number of that subgraph is at least n. Because if you look at the red graph, if the red graph has chromatic number less than n, say at most n minus 1, and the blue graph has chromatic number also less than n minus 1, at most n minus 1. So you have a n minus 1 coloring of the red graph and n minus 1 coloring of the blue graph. Then you put the 2 colors together as coordinates. You color the vertices by the pairs of colors. Then you get the coloring of this graph by n minus 1 square. Right? That is impossible. So this graph, the chromatic number is n minus square plus 1. Okay? So for each I, like this term, like it is monochromatic. Monochromatic subgraph that's called GI of Km. Monochromatic, that means monochromatic under this under Ci. Under Ci, there's a monochromatic graph under this current Ci, Ki with the chromatic number of Gn, Gi is greater or equal to n. So this is what I said. Okay. And then you take the graph G. You take the graph G equals G1 times G2 times Gn, GQ times GQ. Okay. So each of this graph has chromatic number at least n. If the Hedetniemi conjecture is true, then G1 times G2 has chromatic number at least n, and so on. So the Hedetniemi conjecture implies that this graph has chromatic number at least n. Okay, so let's just write here. So if Hedetniemi conjecture is true, if Hedetniemi conjecture is true, then this graph has chromatic number greater or equal to n. Actually equals n. So, but this one of them you can call it that this GI is chromatic number n. Okay, so then what we have? We have okay. Just wait. What we have is this. What we have is this. Is this each GI, then let's write llama here. For all I, to up to Q, this GI is in the image of homomorphism of G, because the product graph is homomorphic to GI. What you do, you just use projection. So the vertices of G are the Q tuples. You just send this Q tuples to the ith coordinate. That is a homomorphism. Okay, that is a homomorphism because two vertices are adjacent if and only if each coordinate is adjacent. So that is a H-preserving mapping. That is H-preserving mapping. And we have so this Kn else this homomorphic image, right? Because no matter how you two-color the edges of Kn, you get one of these GI as a monochromatic subgraph, and that is in homomorphic image. That is in homomorphic image. Okay. Sorry, Km. This is Km. M is n minus 1 squared plus 1. And we just proved that the chromatic Ramsey number of G is necessarily equal to the minimum n, minimum m, such as Km else comma G. Right? That is what we proved in this lemma. We proved this, and this says, because this m is n minus 1 squared, so therefore this says this graph, for this particular graph, is necessarily equal to n minus 1 squared plus 1. Okay, this is necessarily equal to n minus 1 squared plus 1. So what is the problem here? The problem is that we used Hedetniemi conjecture to confirm that this graph is chromatic number n. Is chromatic number n. Okay? And for this step, we use Hedetniemi conjecture. So because Hedetniemi conjecture fails, it's not true. So this graph, we cannot say its chromatic number is n. And also we still have this as this conclusion, but it does not mean to prove this one we need to have a n chromatic graph. We need to construct an n chromatic graph whose chromatic Ramsey number is n minus 1 squared plus 1. We know that if it's n chromatic graph, this cannot be smaller than this number. But we need this necessary equality for a particular graph, n chromatic graph. So without Hedetniemi's conjecture, we don't know if this graph is chromatic number n. Okay, so how do I solve this problem? Okay, I just look at this one. So this one actually, I can get a stronger conclusion. I take all these colorings. I can actually, I can find the GI. So the fractional chromatic number is Kn. Okay, what is that? So actually, it's more than that. So either. So if you look at the edges are colored by two colors, red and blue. So if the the fractional chromatic number, I'm not going to define today. I hope you know it. So that's right here. If I'm going to, I will give a proof of this theorem in another lecture. So I'm not going to state it today, but just I state one property of the fractional chromatic number. So the fractional chromatic number of a graph is greater or equal to the number of vertices of the graph divided by the independence number. This is the maximum size of the independence set. Okay. and it's also greater or equal to the clique number. It's this, not this one, but the whole thing. Because subgraph, if the clique number is, yeah, I'll just that's trivial, so I will not. Okay. So you take the red graph and the blue graph. So you color the Km by red and blue. You take the red graph. So you look at red graph. The red graph either has clique number at least n. Right? Maybe the clique number is at least n. If the clique number is at least n, then so the red graph has fractional chromatic number at least n, right? Because it's complete graph. So this is it's another property. This complete graph is the same as the chromatic number, the fractional chromatic number. I will define in another lecture. So either the red graph has clique number k at least n, and therefore the fractional chromatic number of red graph is at least n, or the red graph has clique number at most n minus 1. If the red graph has chromatic number at most n minus 1, then the fractional chromatic number of the blue graph, that means the clique number of the red graph is the independence number of the blue graph, right? They complement each other. So that means the blue graph has independence number at most n minus 1. Then so that what we get, either let's say the fractional chromatic number of the, let's write this is red graph. Okay, this is red. Let's just write red. Okay, red. So this is the red subgraph. In you two H color this Km. This is the red subgraph. Either the clique number of red is at least k, at least n. So either this is at least n, okay, or the fractional chromatic number of the blue graph. That means the blue graph. If this is not true, then the red graph has clique number n minus 1, at most n minus 1. So the blue graph has independence number at most n minus 1. Then in this case, the total number of vertices n minus 1 squared plus 1, okay, and divided by n minus 1. So this is greater than n minus 1. Okay? This is greater than n minus 1. So from here, what we find? We find so there's a monochromatic graph. The fractional chromatic number is greater than n minus 1. That's what we actually is greater or equal. Actually, is greater or equal to n minus 1 plus 1 over n minus 1. So that's what we can say. And then what I proved? I proved that the fractional version of Hedetniemi's conjecture is true. Actually, I should say this kind of observation was this result. This is observed by Claude Tardif. Before I proved this fractional version of Hedetniemi conjecture, he has this observation. So you don't need to have this Hedetniemi conjecture to imply this. You just need the fractional version of Hedetniemi's conjecture. So this observation is due to Claude Tardif. Claude Tardif. It's a Canadian mathematician, and it's a friend of mine. It's a good friend of mine, but I haven't seen him for many years now. Okay, so what I did, I proved this result. I proved this result. I proved that the this theorem, this fractional version of the Hedetniemi conjecture is true. This is the result I proved in 2011. That's for every graph G and every graph H, the fractional chromatic number of G times H is equal to the minimum of the fractional chromatic number of G and the fractional chromatic number of H. Okay, then you apply this result, this theorem to this graph, then what you get, you get the fractional chromatic number. The fractional chromatic number of G is, because the fractional chromatic, each of them is bigger than that one. You apply so this one, it's this product is associative. You can apply this to, you can apply this to many. The product of many copies is still equal to the minimum. This is 2, but you can extend to many product. So we got, this is the fractional chromatic number is at least n minus 1 plus this number. Okay. But the chromatic number of any graph is great or equal to the fractional chromatic number of that graph. This is true for any graph. Okay. But this has to be an integer. So the chromatic number is, the fractional chromatic number don't need not to be an integer. So this implies it's greater or equal to n. So we don't need the Hedetniemi conjecture to guarantee this. We just need the fractional version. Of Hedetniemi conjecture, then we have this conclusion. Okay, so that is the end of today's lecture. Thank you.